We talked about the interference of monochromatic, coherent light emitted through two thin, closely spaced slits. That's what we talked about last time. Today, we'll talk about another light interference phenomenon, commonly referred to as thin film interference. You witness many examples of this type of interference on a daily basis, okay, from soap bubble films to oil slicks on pavements to anti-reflective lens coatings, okay, to the naturally occurring brilliant colors we see in the animal kingdom. Okay, examples to include butterfly wings, hummingbirds, and peacocks. In today's lesson, okay, we'll explore the cause of thin film interference and apply it to some of these examples that I've just mentioned. This slide should really serve as a review. Okay, these concepts we're going to introduce here, we need in today's lesson, but they are not new. So we're going to be taking a look here at what happens when a wave travels from one medium into another. And as we've said many times previously, okay, when a wave traveling from one medium enters a new medium, some of that wave's energy gets transmitted into the new medium, whereas some of the energy gets reflected at the boundary. And we've talked previously about what sort of wave properties are affected here. Okay, well, when we take a look at the wave equation here, we've said many times that when a wave enters a new medium, the frequency of the wave cannot change. Okay, this would violate the law of conservation of energy if it were to do so. We said that the wave speed certainly can change. Okay, what causes the wave speed to change? We said it's really the delay between the absorption and the re-emission of the wave's energy, okay, as it travels through transparent media. And given these two facts, along with a wave equation, okay, describing wave motion, we can then reason that, okay, if the frequency must remain constant, okay, while the wave speed changes, this implies that the wavelength is going to change, okay, as that wave enters a new medium. And in this lesson, we're going to be talking about waves that are traveling from one medium, okay, and then enter what we call a thin film. So we are going to have to deal with the fact that the wavelength of our light is going to change as it enters, okay, this new medium. So the wavelength change, we've done this before. The only new thing here is that we are going to apply it to a film, but it's the same physics we've discussed previously. Okay, so we start with the fact that when the wave travels from medium 1 into medium 2, the frequency of the wave does not change. Okay, the frequency must be constant according to the law of conservation of energy. When we substitute in our wave equation, okay, and get an expression in terms of wave speed and wavelength, okay, we end up at this point. And from here, rather than talk about the speed of a wave in a medium, we like to, when we're talking about, okay, light, we like to represent wave speed in terms of the indices of refraction. So we will make that substitution using the definition of index of refraction, in which case, this fact that the frequency doesn't change, okay, we've substituted in the wave equation, brings us to this point that, okay, n1 lambda 1 equals n2 lambda 2. And here, okay, solving for lambda 2, that is the wavelength of the wave in the new medium. The only thing we're going to add here is if that new medium happens to be a film, okay, we can write this, and if it's a thin film surrounded by air, okay, which is not always the case, but is very often the case, then we can think of medium 2 as that of the film, in which case, okay, n1 becomes our incident medium, having an index of refraction n sub air. Okay, n sub 2 becomes the index of refraction of the film material, okay, times lambda sub air. Now here, because the index of refraction of air is so close to 1, remember it's 1.0003, it's so close to 1, we can treat it as 1, in which case we see here that the wavelength of our light will change upon entering the film, okay, according to this equation here. It's about equal to its wavelength in air divided by the index of refraction of the film. So we will use this equation, okay, we will use this when we apply thin film interference in the solution of problems. So think back to our discussion of wave theory involving mechanical waves, like for example a wave traveling down a string or a coil spring. And you recall that when a wave traveling in one medium enters the new medium, okay, at the boundary, that reflected wave may or may not experience a phase change upon reflection. In other words, for a coil spring, for example, if the wave encounters a boundary, okay, between the spring and the new material, whether it's your arm or air or whatever, okay, that reflected pulse may come back erect, okay, in the same direction as the incident pulse, or it may come back inverted. So this is what we mean by phase change. It turns out that when we look at light or electromagnetic waves, okay, there's also the possibility of a phase change that can happen upon reflection, okay, when a wave encounters that boundary between the two media. So that's what we need to talk about here, because when we apply, okay, the physics to thin film interference, we need to see whether or not that wave that is reflected at both the top surface and bottom surface or back surface of the film will experience a phase change upon reflection. So in order to talk about, and we talked about for material traveling, mechanical waves traveling through solid media, we said that density is very often the indicator of the wave speed in a medium. When we talk about electromagnetic waves traveling through transparent or semi-transparent media, then we have a similar concept. We can talk about the optical density of the medium. We'll symbolize it here with the symbol rho. And the optical density is really directly proportional to the index of refraction. Okay, the greater a wave will get slowed down in a new medium, the slower that it travels, the greater the index of refraction, and therefore the greater the optical density. So let's review here the phase change conditions from what we know about mechanical waves. So if we look at waves traveling on strings, if a wave travels from a less dense medium to a more dense medium, okay, you recall that the reflected wave did experience a phase change upon reflection. Whereas when the opposite is true, when a wave is traveling from a more dense medium to a less dense medium, okay, the reflected wave experienced no phase change. Okay, the same basic rule applies here to electromagnetic waves. If we just replace density with optical density, when a wave travels from a less optically dense medium, okay, one with a lower index of refraction to a more optically dense medium with a higher index of refraction, okay, then the reflected wave will experience a phase change upon reflection. And of course, when the opposite is true, when a wave is traveling from a more optically dense medium to a less optically dense medium, okay, one with a greater index of refraction into a medium with a smaller index of refraction, there is no phase change upon reflection. This is very important that you understand this if you are going to be successful in solving thin film interference problems. A couple things to note. One, very important, the transmitted wave never experiences any phase change. Okay, we say that when a wave encounters a boundary between two media, some of the wave's energy is transmitted, some is reflected. For the transmitted wave, there is never any phase change. Okay, and secondly, a phase difference of pi radians corresponds to a wavelength difference of half a wavelength. So when we talk about a phase change at the boundary, if the reflected wave experiences a phase change, we can equate that to a phase difference of pi radians, or we can think of it as a wavelength difference of half a wavelength. So in this slide, we are going to explain the phenomenon of film interference by taking a look at a specific sample problem. So let's start by identifying the problem. Let's suppose that we have a thin film, okay, which you see here displayed on the screen, and it has a thickness T, and it is surrounded by air on both sides. Okay, we're going to assume that the index of refraction of the film is greater than air. That will pretty much always be the case. Remember, the index of refraction of air is 1. Whether this film is made of soap solution or oil, okay, the optical density of the film will be greater than that of air. So we're asked to determine the interference conditions. And with thin film interference, you have the possibility of getting, both constructive and destructive interference in your problems. And your goal in these problems is to be able to figure out what those interference conditions look like in order to solve the problem. So let's take a look at the process here that is involved in going through one of these problems and identifying, okay, the interference involved. So the first step is to identify the thin film. Usually that's going to be obvious. And I say here, draw a ray diagram to represent the reflected and transmitted waves at the boundaries. So let's do that. If we have light, okay, electromagnetic wave, which is coming from air and entering the film, okay, this represents the incident wave, the incident electromagnetic wave. And like we say, when that wave encounters the boundary between the air and the film, we know that some of that energy is going to get reflected. So there'll be a reflected wave at the top surface of the film, and there's going to be a transmitted wave as well. When this transmitted wave reaches the back surface or bottom surface of the film, okay, it also encounters a boundary between two media. So the same thing is going to happen. We're going to get a reflected wave at that back surface as well as a transmitted wave. And for the wave that is reflected at the back surface of the film, okay, it now will re-enter a new medium, in which case some of that energy will be transmitted here. And of course, some of it will get reflected. And this process is going to continue. But we can stop the process here because it is really these two waves, okay, that we need to consider with thin film interference. So it is the wave, the ray that is reflected from the top surface of the film or the front surface of the film, as well as the wave which is reflected at the back surface of the film and then transmitted into our incident medium. So the next step is we need to identify the phase changes for the waves that are reflected at the front or top surface of the film and the bottom or back surface of the film. So this is what we talked about before. Okay, this is where you have to use your rules to say whether there will be a phase change due to this change in optical density. So starting with the top surface here, we notice that we have a wave which is traveling from air into a film with a greater optical density. So yes, we would expect that, okay, the reflected wave is going to experience a phase change at that upon reflection. Why? Because anytime you have a wave which is traveling from a less optically dense medium into a more optically dense medium with a higher index of refraction, the reflected wave experiences a phase change. When we look at the wave which is coming here and is reflected at the bottom surface of the film, notice in this case that the wave is going from film to air, okay, in which case we would say that there is no phase change upon reflection. Why? Because we have a wave which is going from a more optically dense medium, that of film, into a less optically dense medium, which is that of air. So there is no phase change upon reflection. Now it is important that we can keep track of these phase changes so that when these two rays finally interfere with each other, where your eye is going to be situated, we need to see the phase difference between them, if there is one. In other words, we need to see whether they're in phase or out of phase with each other. So I'm going to introduce a notation here that's going to help us keep track. And the notation I'm going to use here is just a 0 or a pi. So if we always start with our incident wave, with a phase difference of 0, let's say, we can then keep track of all the phase changes from this point on. So we said that the wave that is reflected at the top surface of the film experiences a phase change. So I'm going to say it is pi radians out of phase with the incident wave. Remember, we said that the transmitted wave never experiences a phase change, so it is going to be in phase with the incident wave. When we look at the back surface of the film, we said that the reflected wave experiences no phase change, and the transmitted wave will never experience a phase change. So here, we see that the reflected wave right here is in phase, with the wave that is transmitted initially. And we can follow this through. When this wave travels from film into air, that transmitted wave will never experience a phase change. So as we see here, the end result is that when these waves end up interfering here where our eye is, we see that they are pi radians, or half a wavelength, out of phase with one another. All right. If the problem does not give you the wavelength of the light in the film, which very often it won't, it'll give you the wavelength of the light in the air but not in the film, you've got to figure that out. You've got to determine that based on what we said on the previous slide. So given that, we're now ready to determine the interference conditions and solve for the unknowns. So here's the part that you got to pay attention to here. And we'll first talk about the case for constructive interference. So let's think about it. When these two waves interfere here, where your eye is, the wave which has traveled through the film and is reflected off the back surface of the film has traveled a greater distance than the wave that is reflected off the top surface of the film. So that difference in optical path length, that greater distance traveled, we need to know what that is. And here's the thing about thin film interference. The way I'm drawing this picture for you, these rays get separated enough that they're not going to interfere with each other. You are typically only going to see thin film interference for near normal angles of incidence. When these rays are much more nearly perpendicular to the interface, or they lie near the normal line, in which case the angle of incidence is very small. The problem with drawing them that way is that when it comes to drawing the picture, it's confusing and hard to keep them straight. So I tend to draw them with greater angles of incidence, but realize that for thin film interference to occur, these rays will have to have much smaller angles of incidence, so they're near normal angles of incidence. In which case, the difference in path length between the ray that is reflected off the back surface of the film will simply be equal to twice the film thickness. For rays that are nearly normal, we'll say that this ray over here that I'm showing with the laser pointer will travel a distance about twice the film thickness greater than the ray that's reflected on the front surface of the film. So that's where this condition over here, this is a difference in the optical path length of these two rays. So when these rays meet, you will see that they are naturally pi radians out of phase, half a wavelength out of phase. So, and remember that okay, pi radians, a phase difference of pi radians is equal to a path length difference of 1/2 of a wavelength. So what we're saying here is that the path length difference between these two waves, if it was equal to, if it was equal to, let's say, 1/2 of a wavelength, then these rays are going to constructively interfere. Think about it. They are naturally 1/2 of a wavelength out of phase due to their phase difference. So to bring them back in phase, we would have to add a 1/2 wavelength to that. So do you see here that the condition for constructive interference, when they meet, they are naturally 1/2 a wavelength out of phase. Okay, we're going to have to add another 1/2 wavelength to that to bring them into phase. So this is what our constructive interference condition is going to look like. The difference in the distance traveled by these two rays, which is twice the film thickness, okay, if it's equal to 1/2 of a wavelength, okay, and then we add the 1/2 wavelength for the natural phase shift due to reflection, they'll now be back in phase. If they're 1.5 wavelengths out of phase, and we add in a 1/2 wavelength due to the phase change upon reflection, they will once again be in phase. So this is how we write our constructive interference condition. Likewise, the case for destructive interference, if we say the difference in the distance that each of these rays travels, the difference in optical path length is equal to a whole number of wavelengths, well, now they're going to destructively interfere, because when you take that path length difference equal to a whole number of wavelengths and you add in the phase difference due to the phase change upon reflection, you will now be adding an extra 1/2 wavelength to bring them out of phase. So you gotta figure this out, okay? You first of all have to identify whether those waves, when they meet, experience any difference in phase due to the phase change upon reflection, okay? And then you have to say, well, okay, they're going to travel different distances. Okay, so you've got to either, you've got to figure out what you need to do to these rays to bring them back into phase. Here we're going to have to, add a 1/2 wavelength to bring them back into phase so they constructively interfere, or do nothing. Okay, in the case where we want to have destructive interference. I cannot stress enough that there is no definitive set of interference conditions when you solve these problems. The interference conditions change with the problem. What serves as the constructive interference condition for one problem can just as well serve as the destructive interference condition for the next problem. These conditions have to be figured out for each individual problem. You cannot memorize them. Okay, so I can't stress that enough. You've got to go through a process like we did to figure out what those interference conditions are. Right, so because I'm into beating dead horses, I'm going to repeat exactly what I ended the last slide with. Actually, the truth is I kind of forgot it was going to be a part of this slide, so I said it anyways, but okay. Always listen to your favorite one-eared rabbit when he tells you that if you want to solve these thin film interference problems, okay, you don't want to memorize formulas for the interference conditions. All these problems differ. Interference conditions will differ too. You have to go through an argument like we did above to determine the interference conditions, okay, by looking at the phase changes at the boundaries. We'll look at a bunch of example problems, and we have to figure out the interference conditions. They cannot be memorized. So some examples of thin film interference that we'll take a look in the problems we're going to look at shortly, and just in life. The iridescent colors that you find naturally occurring in many animal species are due to thin films of oil. Okay, for example, peacock feathers, okay, butterflies, and hummingbirds. Okay, all examples, these bright iridescent colors are formed because of, okay, light interference with thin films. Turns out that the colors that you see will change when viewed from different angles. This is something that we can explain, okay, when we look at the interference conditions. And the multiple colors can be due to varying thicknesses of film. Remember that the optical path length difference, okay, the difference between the wave that is reflected from the top surface of the film and the bottom surface of the film depends upon the film thickness. So different thicknesses often give you conditions for constructive interference of different wavelengths of light. Some additional examples of thin film interference that you encounter in life, okay, are as follows. Newton's rings, this was a problem proposed by Newton, and we have a homework problem on this, so I'll wait, okay, there to actually show you the setup of this, what actually causes it. But you can see here, okay, these are two examples. This is a setup here where you have two glass plates, okay, and if you have an air gap between there, it is not of a constant thickness. The thickness changes, and you can see that that changing thickness leads to the interference of different wavelengths of light causing the different colors. Oil slicks, this is something you've probably noticed when you have a wet pavement, you've got a little bit of oil from a car there. You can see these iridescent color patterns that resemble what you would find in a soap bubble, for example. So you see this on pavement, okay, wet pavement where there's some oil. Air gap between flat glass plates. We're going to actually do a problem not involving an air gap, but involving a water gap, okay, between flat glass plates. Same concept. Okay, so these are all examples of thin film interference. The ones on this slide are a little bit less natural than the thin film interference we see in the animal kingdom on the previous slide. All right, so in this slide and then really the remaining 3 slides of this presentation, we'll take a look at applying this theory of thin film interference in solving some problems. So let's start by taking a look at this example. Here we're talking about the thickness of soap bubble skin. We're told that a soap bubble appears green, and the wavelength of that green light in air is 540 nanometers. Okay, this green light appears on the front surface near the viewer if you're looking at this soap bubble. We're asked to find the minimum film thickness of the soap bubble, okay, in which this green light will be observed. We're told the index of refraction of the soap solution is 1.35. All right, so like we said, we are going to go through these steps here. And I will say we've looked at this problem when as the example problem, when we were trying to discuss the interference conditions. That is, we have a film of soap solution surrounded on both sides by air. So we've already looked at, okay, the ray diagram and okay, the phase relationships for these rays. Okay, but we'll go through this again very quickly here. So we start a problem, we identify the thin film, and we draw the ray diagram to represent the reflected and transmitted waves at the boundaries. So let's quickly go through those. So we have our wave of green light starting in air, hits the boundary between the air and the film, and we said that some of that wave is reflected at the boundary, some of it gets transmitted. And for that transmitted wave, when it hits the back surface of the film, once again the media changes. So once again, part of that energy gets reflected at the back surface, some of it gets transmitted. And for the ray or wave that gets reflected at the back surface, okay, there will be another reflection at the top surface, which we don't really care about, okay, but we do care about that transmitted wave because, okay, it is that wave which will interfere with the reflected wave at the top surface that's going to cause the thin film interference. We need to identify phase changes for the reflected waves at both the top surface of the film as well as the bottom surface of the film. And we will use our phase notation here. Once again, saying that the incident wave starts out, okay, with 0 phase. Like we said, there's going to be a phase change upon reflection at the top surface of the film because we have a wave going from a less optically dense medium, air, into a more optically dense medium with a higher index of refraction, which is soap. Causes a phase change upon reflection. The transmitted wave never experiences a phase change, so these transmitted waves, okay, don't experience any phase change. When we look at the reflected wave at the bottom or back surface of the film, okay, just like we said before, there is no phase change because the wave is going from a more optically dense medium into a less optically dense medium, so there's no phase change. Once again, the transmitted wave, okay, never experiences any phase change. So we have this notation. We see that when these waves meet, okay, they are naturally pi radians out of phase, which corresponds to a path length difference of half a wavelength. We need to determine what the wavelength of the green light is in the film. Notice in this problem, we're given the wavelength of green light in air, but we need to know what it is in the film. So we will use this relationship. The wavelength in the film goes like the index of refraction in the incident medium, which is air, divided by the index of refraction of the film, times the wavelength in air. We plug in our values here, and we come up with the wavelength in the film being reduced from 540 nanometers to 400 nanometers. Okay, we're now in a position to determine the interference conditions and solve for the unknown. So it's important here. We're talking about constructive interference or destructive interference. We'll take a look at the problem. Okay, it says a soap bubble appears green. In other words, we see green light. That corresponds to the condition for constructive interference. Now, remember, when we write down our interference condition, we're saying that the ray that gets reflected off the top surface of the film, okay, will travel a shorter distance than the ray that gets reflected off the bottom surface of the film. When the difference in optical path length, okay, between those two waves is equal to an integral number of whole wavelengths, okay, or 0, then we get constructive interference. But remember what we're saying here is that already that difference in path length is equal to a half wavelength difference just due to the phase change upon reflection. So, okay, right here, the phase change upon reflection causes them to be pi radians out of phase, which is with each other, which is equal to a half wavelength. So if we want to bring them back into phase so that they will constructively interfere, we have got to add another 1/2 wavelength, okay, to them, to the, okay, optical path length difference, okay, if we're going to bring them back into phase. So what we're saying is that, okay, the difference in the distance traveled between these two waves, okay, is already half a wavelength out of phase, so we've got to add in at least, 1/2 wavelength to bring them back into phase. We could add 1.5 wavelengths and bring them back into phase, so now there'll be 2 wavelengths out of phase. We could let m equal 2, we could add 2.5 wavelengths, in which case with the extra half wavelength there'll be 3 wavelengths out of phase, which means they'll interfere constructively. So we've got to figure out that condition here. At this point here, we notice that it says, what is the minimum thickness of the film? So looking at this relationship here, okay, T will be a minimum when M is a minimum. The minimum value for M is 0. So minimum thickness corresponds to a value of M being 0, in which case we can say that 2 times the minimum thickness is really equal to 0 plus 1/2 times the wavelength of, okay, the green light in the film. And solving for T min, we come up with, a film thickness of 100 nanometers. Just want to point out here that the tiniest object seen by an unaided human eye, okay, like this soap bubble skin, is 5,000 times thinner than a human hair or a cigarette paper. So this thin film is probably the smallest or thinnest object that the human eye is capable of seeing. So in this second example problem we're taking a look at, this involves the anti-reflection coatings that are very often put on lenses, okay, to try to reduce glare. So coating lenses, photovoltaic cells, and other critical light gathering components with thin layers of appropriate materials can reduce unwanted reflection, which is what we call glare, through destructive interference. Normally, such anti-reflective coatings possess indices of refraction between those of air and glass. So in this problem, we're asked to consider an optical coating of magnesium fluoride on the surface of a lens. The coating has an index of refraction of 1.38, while the lens has an index of refraction of 1.50. What is the minimum coating thickness designed to eliminate light of wavelength 550 nanometers, which is light near the middle of the visible spectrum? So notice here that our approach is going to be exactly like what we did in the previous problem. We're going to start, well, I say here, note, this problem does not model the one solved above, so can't stress enough that you can't just go straight to the interference condition, because for this problem, the interference condition is different than the one previously. And if you don't go through the process, you're just guessing. You might get lucky half the time, the other half the time you'll be wrong, and hey, a 50% isn't a very good grade, so no guessing. So we're going to start by identifying the thin film, and we're going to draw the ray diagram. Okay, we've done this before. It's the same basic ray diagram showing the reflected and transmitted waves at the boundaries. So our film in this case, our thin film, is this magnesium fluoride coating. Okay, so if you think about light coming in, it starts through air. Okay, it travels through this coating, then hits the glass, which is the lens itself. So we have the incident ray, the reflected ray, the transmitted ray, the ray that's reflected off the back surface of the film, between the film and the glass, and ultimately we get the ray that's transmitted there. So when we try to identify these phase changes here, this is going to inform us as to what our interference condition should be. So we always start with our incident ray, we'll say at phase 0. Since we're going from air into a coating, we're going from an index refraction of 1 to 1.38. We're going from a less optically dense to a more optically dense medium. There will be a phase change upon reflection. The transmitted wave here, no phase change, no phase change for this next transmitted ray. When we look at the back surface of the lens, that is the interface between the coating and the glass lens, we see here that we will get a phase change. Why? Because once again, we're moving from a less optically dense medium with an index of refraction of 1.38 to a more optically dense medium with an index of refraction of 1.5. We do get a phase change, at that back surface. And then, of course, the transmitted ray, there is no phase change. So this is a very different set of interference conditions that are going to result than what we had in the previous problem. We need to determine the wavelength of the light in the film we're considering here. So we're told that the 550 nanometer light, that's what it is in air. If we want to find out what that wavelength is in the film, we've got to make that adjustment here. So when we do the calculations here, we find out that the 550 nanometers, when we divide by the index of refraction of the film, becomes about 399 nanometers. And finally, we're now in a position to write down the interference conditions. So from this problem here, we're talking about destructive interference. The goal is to basically eliminate light. You got to read the context of the problem to see whether you're talking about constructive or destructive interference. We're trying to eliminate light. That corresponds to the case of destructive interference. Notice here that the difference in the path length for the wave that is reflected off the top surface versus bottom surface, okay, twice the film thickness. When these waves meet, they are in phase because there's been two phase changes upon reflection that bring these two rays here back into phase. So if we want to look at the condition for destructive interference, we have to now add a half wavelength to that difference in optical path length to bring these rays out of phase. So our destructive interference condition should look something like this. 2t, difference in optical path length. Okay, we've got to basically say that in the minimum case, we're going to add that half wavelength. The minimum case, the difference in the optical path length would be equal to half a wavelength. That would correspond to the case of destructive interference. Or 1.5 wavelengths or 2.5 wavelengths. So once again in this problem, just like the last one, we're asked to find the minimum film thickness. That is going to occur when we look at the minimum value for m, okay, when m takes on a value of 0, in which case, okay, when we solve here, we find out that the minimum film thickness would be equal to 1/4 of the wavelength in the film, or 99.7 nanometers. I want to point out here that the destructive interference condition for this problem is exactly equal to the constructive interference condition for problem 1. So keep that in mind. You can't memorize this stuff. You got to figure it out. So the last example we'll look at today is a slightly more complicated example, not because the thin film interference problem is any more complicated, but simply because of the geometry involved. So some of the problems you'll find in the homework will be like this. You've got to use what you know about trigonometry and geometry, and in this problem, similar triangles, to be able to get at the solution. So perhaps the geometry will be more complicated to you than the physics itself. So in this problem here, a water wedgie, we have two glass microscope slides, 10 centimeters long. They lie on top of each other. They're in contact with each other on one end, while at the other end they are separated by a very small piece of paper, only 0.02 millimeters thick. Of course, the picture I'm showing you over here does not draw this to scale, right? We need to see what's going on. It says, what is the spacing of the interference fringes seen by reflection? Assume monochromatic light with a wavelength in air of 500 nanometers is incident upon both slides. So our approach to this is going to be exactly the same as in the previous problems. Okay, we're going to start by identifying the thin film and drawing the ray diagram to represent, both the reflected and transmitted waves at the boundaries. It is important to identify the film here because we've got more substances in this problem, right? We've got two glass plates, we've got air surrounding them on either side, and we've got this water film in the middle. So here, the film is going to be this this layer of water that exists between the two slides. You need to identify what the film is because remember, it is, when we're determining our interference conditions, we're looking at light that is reflected off the top surface of the film and the bottom surface of the film. So that's why you have to start by identifying the film, which in this case is water. So let's draw a ray diagram, and now that we know the film, we can draw it, only the rays we're really interested in the problem. So here, our initial incident ray comes into air. We don't care about the reflected ray off that air glass interface because the glass is not the film. The film is a water. So we're looking at the ray that gets transmitted from air into glass. Now we're at the top surface of the film. So we do care about that reflected ray. So we care about this one here, and of course, okay, it will be transmitted up over here to our eye. Okay, for the ray that is going from glass into water, we need to consider the transmitted ray here, okay, because we do care about the ray that is reflected from the bottom or back surface of the film right here. Okay, and then of course that gets transmitted through the glass and then through the air. So, do you see that there's many other rays here, reflected and transmitted rays, but these are the ones we care about. All right, so the next step, we need to identify the phase changes for the reflected waves at both the top and bottom surface of the film. So starting out at phase 0 here, okay, the transmitted wave is in phase there. Looking at the wave that is reflected from the top surface of the film, we're going from glass into water, from a more optically dense medium into a less optically dense medium, which implies there is no phase change upon reflection. So that first ray that gets reflected into our eye, okay, there's no phase change with the incident ray. Let's now take a look at the transmitted ray. Okay, right over here, the one that gets transmitted through the water so that it gets reflected off the back surface of the film. Okay, transmitted rays never experience any phase change, but off the back surface of the film, there is a phase change, right? We're going from water to glass, a less optically dense to a more optically dense medium. So there is a phase change upon reflection, and that ray will now get transmitted up to our eye. So, end result, there is a pi radian phase change between the ray we see that is reflected from the top surface of the film and the one reflected from the bottom surface. So we'll have to take that into account in our interference conditions. So let's determine the wavelength of the light in the film. Once again, you got to know what the film is here. The film is the wedge of water. So we're given what the wavelength of light is in air, which is typical for a problem. So to find out what it is in the film, okay, we find out that the 500 nanometer wavelength in air gets reduced when we divide by the index of refraction of water to only 376 nanometers. All right, we're now in a position to determine the interference condition and solve for the unknowns. Now, in this case here, this film thickness changes continuously. We're going to get both constructive and destructive interference. All we're asked to find in this problem is the separation, okay, of these interference fringes. The distance between the fringes. So we have a choice. We could look at either, okay, the light bands where we have constructive interference or dark bands where we get destructive interference. It doesn't really matter. Okay, I'm going to arbitrarily choose here to look at destructive interference, these dark bands. And like we say here, the difference in optical path length, and I know it's a little hard to see here, but I'm saying that the thickness of the film at this point where we're looking at a dark band, at this point of the interference, the film thickness I'm calling T. We don't know what that is. Notice that the thickness of the film changes continuously as we move from left to right. So at this point, the thickness is this arbitrary value T. Okay, so the difference in optical path length between the ray that is reflected from the top surface and bottom surface of the film at near normal angle incidence will be 2T. Okay, and because these waves, when they meet, are naturally pi radians out of phase or half a wavelength out of phase, okay, then basically we will say that they will destructively interfere, okay, if we keep them as they are. If we do not add any, okay, half wavelengths to them, they will naturally destructively interfere, okay, because of their phase difference upon reflection. So this would be the condition for destructive interference. And now, nothing really new here, but now we need to do some geometry here to be able to solve the problem. Okay, so let's take a look at that. Since the film thickness changes continuously, similar triangles give the thickness in terms of the position x from the end. So notice these dimensions I've recorded here in red, right? Film thickness here at this point t, when you are a distance x from the end, right? That we see that this triangle right here, for this arbitrary point with the thickness t, is going to be a similar triangle for this entire triangular piece here, okay, where the entire length of the slide has dimension L and the thickness at the other end is H. So we can set this ratio of lengths of sides of these similar triangles together to come up with a relation for x. Okay, we see here that, okay, this small triangle here, that, okay, t over x, the ratio of these two legs must be equal to, okay, the same ratio for this larger triangle here, the ratio h over L, and those numbers are given. So we can solve it for t, okay, since our interference condition involves t. So solve this for t, which is xh over L, okay, and when we substitute that in for t to our destructive interference condition, 2 times xh over L is equal to m times lambda film, okay, values of m, okay, being 1, 2, 3, and so on. Okay, then we can solve this for x, plug in our numbers here, and let's plug in these numbers here. So solving for x, we get this expression here. Okay, plug in what the wavelength of the light is in the film. L is given to us. We have to convert to meters. Okay, H is also given to us, converted to meters. We find that x has a value of 9.40 times 10 to the minus 4. Okay, okay, times m. Okay, times m, where m is that order number. So basically, if m takes on a value of 1, okay, we see that x is 9.4 times 10 to the minus 4 meters. When x takes on a value of 2, it's twice that much. So hopefully you would agree that the spacing between the fringes, okay, is just going to be 9.4 times 10 to the minus 4 meters. We're kind of skipping the step. You can put some numbers in for m to get two different values of x and subtract them, okay, which will give you this value 9.4 times 10 to the minus 4 meters, which is the spacing between any two fringes, okay, that you will see.